Hi everybody, welcome to today's presentation. We will be talking about the attacks against encrypted VoIP protocols. My name is Ivica Stipovic. I work for Word Solutions in Dublin as an information security consultant. Here is my email address. In case you have any inquiries, please don't hesitate. First off, I'd like to start the presentation by explaining some fundamental terms and acronyms. VoIP stands for Voice over IP. So it entails not only voice, but also video and messaging that uses IP-based transport protocols for transmission. The next term we need to familiarize ourselves with is SIP, which is a session initiation protocol. It's a voice control protocol. And by this, I mean the protocol that is responsible for establishing, maintaining, and teardown of the call. SIP is one of the predominant VoIP control protocols. I'm not sure if it's the most predominant. I haven't found the evidence for that, but it surely is widely used. However, it is not the only one. So the VoIP protocols are actually a family of protocols. Here are some of the examples of other, like media gateway control protocols is for connection management of media gateways. H323 has now a long history of being established as a well-known and widely spread VoIP protocol. XMPP deals with messaging and presence. And Skype, pretty well known, used by the application of the same name, is a proprietary internet telephony protocol that operates on peer-to-peer architectures. So the point of this slide is just to show you that there are a number of protocols that actually comprise VoIP family. So what applications are using VoIP? This screenshot here is just a small sample of those that are using VoIP. Note, however, that not all of them will be using SIP. As I said in the previous slide, Skype uses its own proprietary protocol, and I think it's either Viber or WhatsApp that is not using SIP, but many others like Blink, Cisco IP Communicator, Jitsi will actually use SIP. So again, the idea of this slide is to show you actually the proliferation of VoIP protocols that happened throughout the last, I would say, 2 decades, and their wider adoption by commercial applications. So let's talk a bit about SIP now, because this is the focal point of the presentation. SIP by default runs as a UDP service over port 5060, and by default it's not encrypted. Its full description is given within RFC 3261, but it's not my intention to go through the numerous features that SIP supports. Rather, I will narrow down the discussion to one particular feature that is important to us, and this is its structural similarity to HTTP. So what do I mean by that? This slide is a deconstruction of a typical SIP session, actually a part of it. So you will see in the upper and the lower rectangles, there are SIP requests, and in the middle rectangle is the SIP response. So by the requests, note that we have a construct made of method, which is in this case register, followed by the URI. It's actually the same as HTTP. So if you replace register with get or post and the SIP with the URI with the HTTP URI, you basically get the HTTP response. Also note that a number of the attributes here in the headers will resemble more or less HTTP attributes. Some are actually the same, like user agent, via, content length, and so on. And the same applies for the server response. Note it displayed the message 401 unauthorized, which again is very similar to HTTP responses. So if you replace SIP with HTTP, you essentially get the HTTP response. Also note it shows the server version just the same way as HTTP servers do. So the point of this is it will allow us to analyze SIP traffic easier. So what are the attributes of a SIP session? There are multiple attributes that SIP supports. However, again, we will narrow down our discussion to those that are important for the authentication mechanism. And these are algorithm, method, username, realm, URI, response, nonce, NCC, nonce, and QOP. The reason why the last three are given in the brackets will be explained a little bit later. So these attributes can be captured within some of the SIP requests, not all of them, some of them, and more particularly within the line that starts with the authorization in the right red rectangle here. So why TLS encryption in the first place? Wrapping SIP or any other protocol into TLS makes it more secure. So exactly the same way as wrapping HTTP into TLS makes it more secure than the native HTTP, the same goes for POP3, SMTP, RDP, LDAP. You will see a number of them usually have S at the end, signifying the secure version. So the interception of encrypted SIP will show obfuscated application layer payload. Only IP, TCP, and UDP header level information will be intelligible. So what do I mean by that? If you intercept encrypted SIP session, you will get something like this. So the first arrow shows you the information that you can read in plain text, and that is up to the layer 4 of the OSI reference model. That means you will be able to read the source and destination IP address and source and destination port in clear text. They're not encrypted. However, the application layer will be. So I will structure the presentation in its two aspects. Its first aspect deals with the interception and decryption only. For unencrypted SIP sessions, we would focus only on the interception for obvious reasons. But in our case, as we're dealing with the encrypted sessions, we obviously need to address both. The second aspect will be SIP password cracking. Again, for unencrypted SIP sessions, off-the-shelf tools will do the job for you. But in our case, the situation is a little bit more complicated. So to tackle this encrypted stuff, we basically have two options. One is we can manually prepare a file for a SIP crack. SIP crack is the existing utility that can crack SIP passwords, but we have encrypted sessions, so we would need to do some manual actions here. The second approach is we will develop our own application to streamline the cracking. And this was the approach chosen here. Let's briefly summarize the plain text SIP passwords attack. Generally, there are two tools, SIP dump and SIP crack. Well, probably there are more, but let's just focus on this example. SIP dump takes a PCAP of SIP session as its input, and it will generate a text file as its output. Now, this output is then taken by SIP crack, which then performs the password dictionary attack. Now, both tools work in pretty straightforward fashion, and if you have plain text SIP, it works okay. Note that SIP dump can also be run in a sniffer mode, in which you tell it the designated interface to which it should listen to, and then it will capture the traffic, the dump for you. So one of the plausible attack vectors that I have chosen for this attack was man in the middle. To make this attack work, there are, however, a couple of prerequisites that we need to deal with. First, we need to build a mechanism capable of intercepting and decrypting TLS wrapped session. Second thing is we need a protocol agnostic proxy capable of decrypting TLS. And third thing, we need to send packets to burp. Why do we need protocol agnostic proxy? The intention here is to construct a scalable mechanism capable of cracking any TLS protocol. So not just SIP, right? This is the reason why the proxy should not be application specific. Second thing is, why do we need burp? As many of you will probably know, burp has very nice and very powerful interface for analyzing and actively modifying HTTPS traffic. And the idea here was to use burp rich feature set of capabilities to actually allow me to play with SIP packets and SIP traffic the same way as I would do for HTTP. So the good news is that burp does the job number one, meaning it's able to intercept and decrypt the HTTPS. The bad news, however, is that the burp does not speak SIP or any other protocol for that matter. So I had to fill in this gap and fortunately found a tool which is medium relay Python script. It's shared via the following link. I highly recommend it. It has some very good explanations of its internals. And this brings us to the solution design. Here is the topology of the proof of concept. So on the left-hand side, we have a SIP client. That's the client that initiates the call. The middle component is SIP proxy, which runs both medium relay and burp. On the right-hand side, there's a SIP server that processes the VOIP traffic and establishes the call to the destination client. Note that we have TLS tunnels established between SIP client and SIP proxy and from SIP proxy to SIP server. That's important to maintain the encryption along the whole path. So in my particular case, I had SIP proxy running both components on a single virtual machine, which was Kali, but there's no reason why you shouldn't be able to split them into, say, 2 VMs, and you can use any Linux. Kali is not a requirement. So now I want to dive a little bit into the mechanics of the interception and decryption so you get the idea how it works. So we run the medium relay by telling it to listen on all of the available network interfaces. Then we tell it there is an upstream proxy running on the local host port 8080. That's essentially burp. Then we tell it to forward all the traffic it receives on its port 5061 to a SIP server. Okay? So SIP server in our case is that 192.168.0.101. We further present the digital certificate that we created for medium relay and the private key that will actually facilitate the decryption of the traffic. So if we now switch over to burp, which is a upstream proxy, we can see that the SIP session is captured in plain text. So note here that the method is post and that the URL has been encapsulated within that /client request to IP and /server response from IP. Now, these are the things that medium relay will do for us, actually will do for burp. And this feature allows burp to move SIP traffic back and forth. It basically encapsulates it into a HTTP request. So again, the mechanics goes from SIP client that establishes the call via medium relay. The traffic then goes to burp suite then to SIP server that processes the call and establishes the call with the destination client. Note that at this point in time, we have burp fully functional and capable of moving SIP packets back and forth. So this is now the time where you can mount multiple attacks against SIP. If you, for example, turn the burp intercept on, you can send those SIP requests to burp repeater and then change call destinations, brute force destination numbers, change user agent fingerprint, inject some funky headers, and try to establish covered channel from within the SIP headers, spoof calling ID, you name it. Even though the tampering in burp is interesting, none of these attacks here were in the scope of this project. So I focused solely on the password cracking. And this brings me to a second part of the second aspect of the presentation, which is the new application. First, why is this new application required? Why can't we use SIP dump and SIP crack? SIP dump will not work here. We have dumped the decrypted session into a non-PCAP format that SIP dump simply doesn't understand. Additionally, SIP dump has no way of importing the private key to decrypt the PCAP. Remember, we can run the PCAP session on the attacker's proxy. It will be originally encrypted, but since we have access to the private key, we end up with decrypted PCAP session. Wireshark supports that, SIP dump doesn't. So what will be this new application doing? The new application will simply process the output of a MITM relay, which is more or less text file. It will extract the attributes from this output file, which are relevant for the authentication process, and then will perform password dictionary-based attack. So the SIP crack 2 is the name I have chosen for this new utility, actually maps the functional aspects of SIP dump and SIP crack into one single utility. And by having this, it streamlines the whole process of password dumping. Otherwise, we would need to do some manual manipulation of the file to make SIP crack, the old version, to work with it. But it's more elegant when you have streamlined operation. So how do we crack digest algorithm? There is nothing particularly magic about it. This digest algorithm is published within RFC 2069 and RFC 2617. The most important difference for us is the introduction of those three attributes, QOP, NC, and CNONs. They were introduced as part of the RFC 2617 and with purpose to increase the security of the digest authentication. They essentially add some variability into the MD5 hashing, but for us, it really doesn't matter because we have a way how we can intercept, decrypt them, extract them, and put them into the cracking algorithm. So how does this digest authentication look like? If QOP, CNONs, and NCs are not defined, then we are dealing with RFC 2069 compliant behavior. And in that case, H1 is calculated as MD5 hash of username, RAM, and password. H2 is MD5 hash of method and URI. And final response is MD5 hash of H1, nonce, and H2. Now note that the response here will be on one hand calculated in our cracking algorithm, and on the other hand, it will be extracted from the SIP response, and then they are compared. If they're the same, we have found the password. If QOP, CNONs, and NCs are defined, then the SIP proxy is working according to RFC 2617, and in which case response is calculated in a slightly different manner. Note that H1 and H2 are defined the same way for both RFCs. Anyway, long story short, this URL gives you the access to the source code of my humble application, so feel free to have a look. It's pretty straightforward. Final thoughts. So there are a couple of things I wish to explain. One is the development. SIPCrack 2 is currently application developed for Linux only. It's written in C and compiled for Linux version, for Linux architecture, but I do hope to release the Windows version with CUDA multi-threading and parallel processing in the near future. Given that I'm a pretty bad programmer, that can, take some time, but I hope it will eventually show up. For those less familiar, just briefly, multi-threading and parallel processing is a method where you offload the processing of the main CPU onto the graphical processing unit. So if you have a powerful graphic card like, say, NVIDIA GeForce, you should be able to achieve significant acceleration in the brute forcing mechanism, but we'll see about that. Second thing, how realistic or difficult is this attack? Even though the presentation shows that, we can essentially attack the encrypted VoIP protocols, it's not so easy in the real life scenario. And the reason for that is following. The assumption of this attack is that we don't have control over the legitimate client, over the legitimate SIP proxy, or over the legitimate SIP server. So the question that arises is, well, how do we get the traffic in the first place? There are ways how to do it. ARP poisoning is one of them. ARP poisoning is a method where you inject specially crafted ARP entries into the switch cache, making it forward the traffic to your component instead of the legitimate one. ARP poisoning is relatively easy to implement in a lab environment, but very difficult in real case scenario. You would need to compromise the service provider infrastructure to allow that ARP injection. And that's not an easy task. So this leads us to the recommendations. Use strong passwords. The more complex passwords you use, the less likely they will be found in the dictionary files that attackers are using. Do not use self-signed certificates. If you do, you make the job for the attacker easier because it becomes easier to impersonate your legitimate components. The third thing is, I recommend using the client-side certificate in addition to server-side certificate. So what you make here is you essentially make not only client verify the legitimacy of the server, but also server checking the legitimacy of the client. Obviously, that two-way check is more secure than one-way check, but it comes with the cost, and the cost is additional burden to your PKI infrastructure. Given all that together, I would rate this risk as medium. So we'll switch over now to demo, so you get the impression how things operate in real, in the lab environment. We will focus here on the attacker's component, which is the central screen. We run the Meton relay with all those attributes that I have explained. The only difference is this time we dump its output into the text file. So we run that, and what happens now in the background is I'm starting a couple of VoIP clients. They will soon show up, so you'll get a better picture. But what actually happens here is these clients will register themselves with the SIP server. And the registration process is the one that requires the authentication. that authentication details will be captured by the meter relay. So this is how it looks like. Basically, we have two accounts. One has saved password. The other one will look for the password to be entered manually. And this process here performs that registration with the SIP server. Now, at this point in time, we should have enough information captured by the meter relay and decrypted, what is even more important, to actually do the attack. What I want to show you here is the running TCP dump session on the SIP server. So the SIP server here is asterisk, and the reason why I'm showing you this is that you can notice there is no intelligible information here, nothing in human readable form, except for those layer 1, 2, 3, and 4 information, which means, yeah, you still can see the IP addresses and the ports, both source and destination. But in the column on the right-hand side, you actually don't see any human readable text. And that makes sense because, as you can see here outlined, the session is TLS, so encrypted. That's what I wanted to show on this side. So now we can actually interrupt this session and have a look at the output file. You can see it's a text-based file that captured the SIP session in the plain text. It contains some other attributes, but it's really it's not relevant for us. And now the only thing that remains to be done is to run SIP cracker against the captured file. So if we run that, it will hopefully find the credentials. But if we switch over then to burp, you can actually see the whole session being captured in the plain text. Even though, as I said, I did not perform any other SIP attacks, this model here gives you actually the opportunity to interfere with the traffic. So if you turn the intercept on, you can actually actively modify that traffic. So the only thing here I wish to draw your attention to is that line which shows those attributes in a clear text. And as I said, I leave you for homework to play with other SIP attacks, but that is essentially all that I wanted to show you on the burp side. Again, the output of the tool is pretty simple. It displays the username and the password. If it finds any, and it takes two input arguments. One is the output file of a meter relay, which is sipdemo4.txt. The other is a password file. And that concludes my presentation. I left full 10 seconds for questions, so if you have any, fire them up.
Thank you, Ivica, for your talk. Ladies and gentlemen, another reminder: the slides will be posted immediately or almost immediately after every talk. So do download them and share them with your friends.